Well, hey everyone, welcome back to Lecture 4E. In this lecture, we are going to talk about a phenomenon called sp mixing. Now, earlier we had talked about how the sigma bond formed between the p orbitals goes higher in energy than the pi bond between the p orbitals. And it's something that's unexpected, and it is due to this phenomena of sp mixing. So let's take a look at this. And so in period 2, this is fairly prevalent, and it cuts the periodic table pretty much in half. So here we have boron, carbon, nitrogen, where the sigma 2p is higher in energy than the pi 2p. And that's not what we would normally expect. Normally, a sigma interaction would have a greater overlap and therefore a lower energy than a pi interaction. But we don't see that happening for these smaller molecules in period 2. Now, the reason that happens is because your smaller molecules have energies between the p orbital, the two p orbitals, and the two s orbitals are closer in energy than they are for the larger atoms, larger molecules such as O2, F2, and neon. So B2 and C2 and N2 have their s and p orbitals closer in energy, and that allows the 2p and the 2s to mix, and we'll see what that does to the energy here in just a little bit. Now, if we look at the molecular energy ordering, we'll see a diagram here, more of a full diagram from what we just saw. So if we look at the sigma 2s, sigma star 2s for boron, carbon, nitrogen, it's exactly what we would expect. But here we see that we have the sigma 2p higher in energy than the pi 2p. Now, the pi star and the sigma star, they have an order that we would expect, because this is generally a very symmetrical type diagram, just like we see over here for the larger atoms. But the problem is that this sp mixing causes this orbital to go up in energy. It actually also causes this one to go down in energy a little bit. So let's see how this happens. Again, this is the diagram that we would expect, but it's not the diagram that we get for those smaller molecules for boron, carbon, and nitrogen. So let's look at the atomic orbitals and how they interact to form the molecular orbitals between the two s's and the two p's. So for our two s orbitals coming together to form the sigma 2s and the sigma 2s star, two s's look like that. And for the sigma 2p, you have the 2pz orbital here and another 2pz orbital here, and they come together and overlap there. Now, if you'll notice, it looks like these two setups of orbitals have very similar symmetry. And as it turns out, the molecular orbitals have the exact same symmetry as each other. Because they have the same symmetry, that gives them the opportunity to mix. They also have to be fairly close in energy. So it turns out for those lighter atoms, boron, carbon, nitrogen, the energies of the sigma 2p and the sigma star 2s are actually close enough in energy that those two molecular orbitals can mix. And they mix in such a way, just like our atomic orbitals do, that it drives one energy down and it drives one energy up. And the reason they do that is because we still use an LCAO type interaction where you have an additive interaction that brings energy down and a subtractive interaction that puts energy up. Let's look at that in a little bit more graphic manner here. So here we have the additive interaction between our two PZs and our two S's, and we can see that they're going to overlap like that. And when they interact, they're going to form an orbital that looks something like this. Now, even though this is actually an anti-bonding orbital, so this isn't completely correct, but I wanted to show what happens if they're in phase. But what happens is you do get a little bit greater interaction between the orbitals, and that leads to a decrease in energy. But more importantly, and this is the one we really want to look at here, is for the bonding orbital of the sigma 2p, the overlap of this orbital in a subtractive manner decreases the lobes here. And so that lowers the amount of interaction for that sigma 2p. And so if you lower the amount of overlap and you lower the amount of interaction, you're going to increase the energy compared to what it would have been if this subtractive interaction was not in place. When we start looking at molecular orbital diagrams and labeling them, we'll see that this actually is what's called the 1 sigma U, and this is what we call the 2 sigma G orbitals for boron, carbon, and nitrogen. So the impact that this has, here we see this 2 sigma G, and here we see the 1 sigma U. We see that as we go to heavier atoms, the energies of the various atomic orbitals, even though this is essentially the same one, they all start to decrease. And the reason for that is because you have a greater charge in the nuclear core as you increase the number of protons. And so those electrons start getting attracted more. Remember, attractive interactions lower energy, so that as we go across the periodic table, our atomic orbital energies start going down, and if they go down, our molecular orbital energies will also go down. So, but look what happens here. Remember our 2 sigma G orbital here, that is the interaction between the two p orbitals, so that's our sigma p interaction there. And we see that it's above that first pi bonding interaction. So as soon as we start getting into p orbitals right here, one of the bigger impacts that we have, and the reason there's 2 lines is because there's 2 p orbitals there, so they're degenerate. What we really have here for boron is two electrons that are each going into 1 molecular orbital. So we have 2 molecular orbitals here, each with 1 electron in there, and that gives us a paramagnetic situation because we have unpaired electrons. If this 2 sigma G had been lower in energy, that's a single orbital. Both of these electrons would have gone in that orbital, and boron would be diamagnetic. But it turns out B2 is paramagnetic, and that's one of the reasons we know that this calculation is correct. So C2, we just put in 2 more electrons. They both occupy the 1 pi U. We get to nitrogen, and these energies are getting closer and closer. And because this interaction is getting pulled closer and closer to the nucleus, and so it's dropping in energy. The pi's are a little more diffuse, so they don't drop in energy quite as much. As we go from nitrogen to oxygen, notice that the molecular orbital for the 2 sigma G drops in energy here. And what we get now is for oxygen, we have the sigma interaction lower in energy than the pi interaction. And then that difference just becomes greater and greater as you push farther to the right in the periodic table. So now we want to ask ourselves, is it diamagnetic or paramagnetic? We do have to consider where we are in the periodic table and what is the order of our orbitals. If we want to look at boron, carbon, and nitrogen, we have to factor in that really large 2s, 2p interaction because it changes the order of the sigma 2p. And so that makes boron diamagnetic. Okay, and then if we come over here from oxygen, fluorine, neon, we see that the sigma 2p is back to being down here, and it doesn't really impact how these fill in, but it does change the order in which our electrons fill in.